Alright, going on to example number 2.3.6. I'm just going to read the question for you. A shaft 1.5 meter long, supported in flexible bearings, okay, at the ends, carries two wheels, each of 50 kg mass. So these are the wheels. One wheel is situated at the center of the shaft and the other at a distance 3.75 meter, 75 mm from the center towards left. Alright, the shaft is hollow, of external diameter 75 mm and internal diameter 40 mm. So you need to make sure, you need to note that this is not a solid shaft but it's a hollow shaft. The density of the shaft material is given 7700 kg per meter cube and its modulus of elasticity is 200 giganewton per meter square. So find the lowest whirling speed of the shaft taking into account the mass of the shaft. Okay, so what all is given in the problem? We will see the length of the shaft is given. It's a hollow shaft. There are two wheels on the shaft of 50 kg each, and the distance, one is at the midpoint and the other one is 0.375 meter from the left side. Okay, then the diameter, internal diameter, outer diameter is given. I'm going to convert everything into meters, and the density of the shaft is also given, and Young's modulus is 200 multiplied by 10 power 9 Newton per meter square. So the question says calculate the whirling speed considering the weight of the shaft. So there are 2 point loads, that is the wheels, which are acting 50 kg and 50 kg at the midpoint and at another point. Alright, so I'm going to name those points as C and D, which will be easier to explain. And we need to consider the weight of the shaft. So it's a uniformly distributed load. So you can add a uniformly distributed load throughout the length, denoting the weight of the shaft. Alright, so you have, so in this particular diagram, you can calculate the natural frequency of vibration, transverse vibration, and that will be, how will you calculate that? Using Dunkerley's method. So first step is to calculate the moment of inertia. So pi by 64, it's now going to be just d power 4. It's a hollow shaft, so d1 minus d1 power 4 minus d2 power 4, all of you know that. So we'll just substitute the values. So d1 is 0.075 square minus 0.04 square. Okay, so and the value is 1.4 into 10 power minus 6 m power 4. Okay, so now density of the shaft, so we've calculated the moment of inertia. Now density of the shaft material is given. We should calculate the mass of the shaft. So note, the weight of the shaft is not given, mass is also not given, but density is given. So you can calculate the mass of the shaft by multiplying area and length and density. So this is also very familiar because in strength of materials class we have learned how to calculate the mass of the shaft. Okay, so I'll just substitute the values here. So pi by 4 d1 0.075 whole square 0.04 whole square multiplied by length 1.5 multiplied by density 7700, and you'll get the value as 24.34. So please calculate and check whether you're getting the same answers or not. Alright, now the next part is to calculate the static deflection of load at C, at D, and the uniformly distributed. So this will become delta 1 at C. So W A square B square by, this is the formula which we've used before also. So first thing is, W is not given, so we'll take it as mg. M is 24.34 kg. Alright, and G value, you'll be taking it as 9.8, and A is taken as 0.375 meter, and B is value from point C to HP, and this is AC, and that is taken as 1.125 meter. Alright, so let's substitute the values. 20 okay, so this is not 24.3, it should be 50 kg, because we are taking the mass of the first load, that is a point load. This 24.3 is for the uniformly distributed load, that is the weight of the shaft. Okay, so please take it as 50. So 50 multiplied by 9.81 multiplied by 0.375, 1.125 square divided by, the rest remains the same, 1.4, and the length is 1.5. So if you calculate this, you will get 70 10 power minus 6 meters. Similarly, do the same thing for deflection at D. So the mass is 50 kg. A is 0.75 on the left side, and on the right side it is 0.75. It's at the midpoint, so it's pretty simple. 50, 9.81, 0.75 whole square, 0.75 whole square divided by E, I, and the length. And if you calculate this, you will get 123 into 10 power minus 6 meter. Now comes, so there are only 2 point loads and one UDL, uniformly distributed load. So what's the formula for a uniformly distributed load? 5 by 384 multiplied by W L power 4 by E I. Okay, so 5, 384. We know the mass. So mass is 24.34 multiplied by 9.81, and the length is 1.5 whole square divided by value of E, 200 into 10 power 9 multiplied by 1.4 into 10 power 6, which is the I. So you will get the value as 56 into 10 power minus 6 meter. So from Dunkley's method, the formula for natural frequency of transverse vibration is equal to 0.4985 divided by root of delta 1, 70.9 into 10 power minus 6, delta 2, the value for delta 2 is this one, plus delta S, 56 into 10 power minus 6 by 1.727. So you need to just substitute all the values and calculate using your calculators. So you get 70 into 10 power minus 6 plus 123 into 10 power minus 6 plus 56 into 10 power minus 6 divided by 1.27. So you should get the value in hertz. Calculate this and you should get 32.4 hertz. But the question is not asking for natural frequency of transverse vibration. It is asking you the whirling speed, lowest whirling speed of the shaft. So that is nothing but the critical speed of the shaft. So the critical speed will be exactly same as the natural frequency but in RPS. So if you want to give the value of the speed, generally the value is given in RPM, revolutions per minute. Just multiply, same thing, 32.4 multiplied by 60, you will get the whirling speed of the shaft. Alright, so now so you have learned about how we calculate natural frequency of longitudinal vibration and transverse vibration. So this comes under free vibrations. So we have forced and undamped. So with this lecture, we will complete how to calculate the natural frequency for a longitudinal vibration and a transverse vibration. In case of transverse vibration with one or more than one load, both point load as well as UDL. Thank you.